Hi guys, Mark again from Harwell XPS. I know we promised some new videos coming out soon, and our first one back. Unfortunately, we had some technical issues with the audio, so thanks to George Major for pointing that one out. We're back again with the same video, hopefully this time with sound. So we're going to be talking about component indexes, something I find very useful when working with bigger models and big data sets. So we're going to look about how these can be used, what kind of things you can do with them, and how they can be useful, hopefully for you, in your data analysis. So I'm going to head over to Casa now, and we're going to start by looking at Syria. So we're not going to go into too many details about the actual fit here. We've already got a video on this, and we're most likely going to be doing some more stuff on Syria soon. So this is just a good example because there's lots of peaks. It's quite a complicated model, and component indexes can really help us not only build these models but display them as well. So the first thing I'm going to do is come up to display parameters, that's F6, and come to the colors tab. So there's a few options here. In fact, if we just quickly go to the components in quantification parameters, the first thing I'm going to just highlight is that we've got our 10 peaks all in all, so 6 peaks for Cerium 4, 4 peaks for Cerium 3. Cerium 4 peaks have been given a component index of 1. Cerium 3 has a component index of 2, so that's this last editable box at the bottom here, just above the asymmetry index. So we've categorized our peaks based on whether they relate to Cerium 4 plus or Cerium 3 plus. So now if we come back to our display parameters, come into colors, we've got one box here that says color the components using the component index. And if I click that, you'll notice that these peaks have all changed color, relating to whether they are Cerium 4, Cerium 3, component index 1, component index 2. We can then combine. So if we combine these peaks with the same component index, we now don't have individual peaks. We've now got these kind of envelopes of the 6 peaks for 4 and the 4 peaks for 3 combined into a single line shape. So now it looks a lot more like linear combination fitting of these two different line shapes. And then finally we've got fill the combined components, and that will do exactly what it says on the tin. So now we've got some nice colourful peaks with the 4 plus and the 3 plus really easily identified by eye. Right, now back into our components tab. So the first quite useful tool that I'm going to show you all, this relates to when you're starting to build these models in the first place. So for example, say you're working on something like this, or you're working on a model where you've got a couple of components combined into a single one, but you've got other peaks in there. You can separate everything out by component index. And whenever you do the kind of the mass linking tools, so for example, firstly I'm just expanding the limits on these peaks, so I can change all of these peaks. So completely meaningless, doesn't mean anything at all. However, with those changed, so for example you've done this fit, whether it's based on some literature theory or whether this is an empirical fit. If we use the lock function and hit enter, we now get these peaks all locked as the ratios, again whether they've been derived from a paper or whether you've derived them from an empirical fit. You use the lock and you've now got a line shape where the 4th maximum ratios will change. So if you're applying this to other materials, other spectra, where you might have slightly different peak widths based on whether that's an instrument effect or whether that's some slack charging effects, etc., you can at least keep all the ratios of your 4th maxima the same. There's also the link function, which will set all of these to g times 1. So, you know, if you're working with things like doublets, where you want to keep the full without maximum the same, or working with things like polymers where you don't really expect the full without maximum of the carbon to change dramatically, and you can use these to reduce the amount of variables in your system, lock the full without maximus together. You can then apply this across the board. But if we come back to our Cerium 4 Plus models, you'll see that none of what we've just done has affected anything here, and that's because it only applies to things with the same component index. So really nice and useful tool. Say if you are building these models and you want to do some peak width fixing or some position fixing or area ratio fixing, you can do all of that just within that component index. Now, if we come up to the line shape, so another thing you might want to do is change the line shape based on, again, theoretical models or things that just aren't quite fitting the way you want them to. If we come up to our line shape, put the hash key in front of the line shape and hit enter, and that will bring up a little dialog box that says, do you want to apply this to all of the line shapes within this component index? And now if we look across, we can see that we've updated this line shape for all of these within the Cerium 3 Plus, but again, our Cerium 4 Plus is unchanged. If you use the equals key and hit enter, you will then apply that to all of the line shapes in the model, regardless of component index. And as you can see, the result of that is our model now looks rubbish because it's got all of the wrong line shapes in. So I'm just going to come down to these. We've got the same model in them all the way down to the bottom. So if I come to this model, control and click on the one I've just changed to highlight it, right click, propagate the components. Now we've just undone all the changes we've put in there. So the final very useful thing, like I say, these looks very nice now. We've got something that is presentable, but you may want to take this across into Excel or Origin, however you want to display your data. And the component indexes again give us a really useful tool for getting this across. So if we open our clipboard, just copy all of this to clipboard, and then I'm going to open up Excel. Again, don't think I'm a Luddite for this. You can use whatever you want, whether that's Origin or Excel. Some people have very strong opinions about which to use. But if you've ever done the, used this clipboard procedure before, you can see that we've got all of our components in here, and at the end, we've now got two columns which aren't usually there, called component sum 1 and component sum 2. Now this relates to the sum of all of the Cerium 4 and the Cerium 3, exactly as we have in Excel. So I'm just going to remove the stuff that we're not too interested in, basically the 10 peaks. Normal and the residual I don't really care about at this point either. So if we put in a line, there we go, just make this a bit bigger, and then you format this however you want, of course, but the important thing to know is that we do have only the envelopes of the Cerium 4 Plus and the Cerium 3 Plus, which again just makes it a lot easier to present these and kind of make it obvious what you're showing when you're showing something like Cerium, where you've got 10 peaks. It's not the most obvious graph to show, because unless you're very familiar with this particular aspect of XPS, 10 individual peaks is much simpler to use. 2, you can show exactly, okay, this is Cerium 3, this is Cerium 4, bang, we're done. So let's get rid of Excel again. There's one other thing I wanted to just quickly go through on again why I think component indexes are very useful, and that's using the model from a reference sample to process something where you have combined elements in here. So for example, here we've got platinum on aluminium hydroxide, so this is just pure aluminium hydroxide from the box, and then we've deposited a bit of platinum on it. Very common in catalysis to have these overlapping, so it's good to know exactly how to best analyze these. So first we're going to stick in our region, make it nice and wide because we're going to be propagating this down to the platinum shortly. So I'm going to create 2 regions. We'll give these a component index of 1, and then our doublet separation should be about 0.41. Fit, beautiful fit, as we would expect. This is just pure aluminium hydroxide, not really much of interest in terms of the actual model fit. What we're going to do is apply some limits to this. So with the hash key in column A, as you can see in column B, we've already got everything locked to A, so that we don't need to worry ourselves about column B. But in column A, I'm going to take the hash 0.1, and that's just going to update the limits of our forward half maximum plus or minus 0.1, just to give us a little bit of wiggle room in the fit, and do the same for the position. So again, plus or minus 0.1 kind of accounts for any small errors in calibration. This is an insulating sample, of course, so, and the same for the forward half maximum, just gives us a little bit of a margin for error to account for maybe any differences in conductivity between the 2 samples, maybe one slightly charged more than the other. So we have these limits, but now we've got something where if we just close this, highlight our platinum on aluminium or alumina hydroxide sample, right click, send our regions and components down, and the overall shape of our aluminium to peak isn't really going to change because we've set those limits, we've locked everything in place, so we have a nice and self-consistent model. So if we reopen our quantification parameters, create a second doublet, this time we're going to rename this to platinum 4F. If you go down to the RSF column and use the hash again, hash is like the super key in CASA, does pretty much everything. Because we've renamed this to platinum 4F, we can use the hash. That will dig out the RSF from the element library. When we put in the create times 2, CASA thought this was a p orbital, so we just need to update our area ratios to account for it being an f orbital, and then we're going to lock our doublet separation 3.35. So change the component indexes again. What I'm going to do is just change aluminium to a higher. So if you change the component index to a higher number, it will give it precedence over a lower number in terms of the visualization of the peaks in the spectra. So if you do want to use these for presentations, etc., then you can just change the number in here to change the order of appearance. If you hold Control, that was just me trying to remember what the shortcut was. If you hold Control and left mouse button click on the component index name there, you can actually come into a color indexer here, right click on the color you want to change, and you can bring out any colors you want. So for example, what do we have? 2 and 1, so let's change this to red and blue, and now turn back on our component indexes. Again, you can change these colors to whatever you want, and present them here, or you can take this across into Origin Excel, whatever you want. So the last thing we need to do is to just update this line shape, because this is platinum metal, so we've got some asymmetry. So if we hold Control, click on our line shape list, we've actually got a fit that was done earlier based on the platinum metal standard. I'm going to load this one up, use the hash again to propagate our line shape. Click fit, and now we have a very nice model where we have our aluminium 2P with all of the peak parameters derived entirely from that aluminium hydroxide standard, and the platinum 4F where we have a known line shape, we've fixed all of our components, etc., and we're able to lock these and display them as fixed components. And you can do the same, for example, if you're adding things like platinum hydroxide, platinum oxides, etc., do the same, different component indexes to help visualize and pick out different platinum species, and keep all of your models consistent, self-consistent, and nicely displayed. So hopefully you will agree that some of this, at least some of this, is quite useful for your fits. I know Neil's just done a number of really awesome videos on the Castle XPS YouTube channel, which covers some of this, so I will link to some of those in the description below. But thanks for watching, and any questions or anything, stick them in the chat box. We will try and get around to answering them whenever we see them, and we'll see you soon for some more videos. Cheers.